Okay, we're going to go ahead and look at what we call binomial distributions and binomial settings. And so what we're going to look at is when the same chance process is repeated several times, we are often interested in whether a particular outcome does or does not happen on each repetition. In some cases, the particular number of repeated trials is fixed in advance. So we know in advance how many trials we're going to do. And we are interested in the number of times a particular event called a success occurs. If the trials in these cases are independent, and that's going to be very important, and each success has an equal chance of occurring, we have what we call a binomial setting. So how do we check for a binomial setting? So we check for it by using this idea of bins. And we can check to see if it's binomial by checking the bins. So the B means binary, and that means the possible outcomes on each trial can be classified as success or failure. For example, I could take our class, and then I can look at a success as the person I choose has an A in the class, and a failure is the person I choose does not have an A in the class. So I've got multiple options, but I look at success and failure. Success is what I want. Failure is what I don't want. And it doesn't mean that you're a failure if you don't have an A. It's just using that as an example. Now, I stands for independent. So the trials must be independent. That is, knowing the outcome of one trial must not have any effect on the outcome of another trial. So a lot of times when we are choosing things, if we're choosing people in a class, for them to be independent, I should be able to pick the same person again. So if I'm picking people for extra credit, I could choose George the first time, and I could choose George again. And so George just gets lucky and gets double the amount of extra credit. And so to be independent, we would have replacement. If we have no replacement, then they are not independent, and so then that violates our binomial condition. The next one is number. So we have to make sure the number of trials must be determined in advance. So we don't just decide, oh, I'm going to do 20 times, and then, oh, no, I'm going to do 25, or no, that's too many, so I'm only going to do 10. So you determine in advance, I'm going to do 10 trials, and you stick to that number. And then S means success, which is on each trial, the probability P of success must be the same. So this is kind of comes from independent, because if they are dependent, then that probability is going to change. Each time I pick a person, the probability will change for the next person if I don't get to pick them again. So non-replacement means that they're dependent, which then will violate the success condition also. So these are our 4 conditions for a binomial setting. Now, we also have a binomial distribution. The count X of successes in a binomial setting is a binomial random variable. And so with a random variable, we now can have a table of probability, and that gives us a probability distribution. And so now when we're looking at this binomial distribution, we have N is the number of trials, and P is the probability of success on any one trial. And now because this is a random variable, but it's a discrete random variable, our values of X, or the number of successes, because I'm counting it out, they're only whole numbers from 0 to N. So now we're going to go ahead and we're going to go through and we're going to check situations to see if they're truly binomial settings. So my first one's already done up for me, so I'm just going to kind of walk you through. We're going to shuffle a deck of cards. We're going to turn over the top card, and X is going to be the number of aces I observe. We're going to put the card back in the deck so we have replacement. We're going to shuffle again, and then we're going to repeat it, and we're going to repeat it 10 times. So is it a binomial setting? So we check our bins. So success would be getting an ace, and failure would be anything but an ace. So that is our binomial setting. I've got a success or failure. There's just one or the other. So we're good here. I, independence. Well, since the card is replaced, each choice will be independent. N, the number of trials. We determined in advance the number of trials was 10, so we've met that condition. And then success, the probability of getting an ace, which is my success, is 4 out of 52 or 1 out of 13 every single time. And since that's consistent, that means yes, this is binomial. So now we're going to walk through one together. We're going to choose 3 students at random from your class. Let y be the number of students who are over 6 feet tall. So binomial, our success is over 6 feet tall. Our failure, not over 6 feet tall. Okay, I, independent. So, is it independent? Did it say that I get to choose a person, put their name back in a hat, and get to choose them again? Since they didn't specifically say, we can't assume this is independent. So there is no replacement. Not independent. And so this is not binomial. And it violates the independence condition. Okay, next one, flip a coin. If it's heads, we roll a 6-sided die. If it's tails, we roll an 8-sided die. Let W be the number of 5s you roll. Repeat this process 5 times. So let's see, success is we roll a 5. Failure roll anything but a 5. Independent, well, the coin doesn't have a memory and the dice doesn't have a memory. So what I roll before doesn't affect what I roll later. So it is independent. N, the number of trials set in advance, the number of trials was 5. And success. So the probability of success let's see, so if I flip a heads, my probability of success is 1 out of 6. And if I get tails, I have an 8-sided die. So a 1 out of 8. And since these are not the same probability, meaning my probability of success is not the same, we have violated the condition of S. The probability of success has to be the same each time. And so that's really what we're looking at when we go through there, because if we don't meet these rules, then we can't use our probability distribution to figure out what the probabilities are. Okay, so now that we can tell if something is truly a binomial distribution, then we can actually calculate a binomial probability. So before we can calculate a binomial probability, so the probability of having 4 successes or 5 successes, we have to talk about this binomial coefficient. And the binomial coefficient tells us how many different ways we can get 2 successes, or how many different ways can I get 4 successes. because I can easily calculate the probability of getting 2 successes, but I need that for every single time I'd have 2 successes. So I have to figure out how many different ways can I have those 2 successes, and that's our binomial coefficient. And the way the binomial coefficient looks is on our formula, it looks like this. Parentheses with n on top and k on bottom, where n is the number of trials and k is the number of successes. And what that really ends up looking like, so that's just a notation for n factorial over k factorial times n minus k factorial. And what this really is this is a combination. So you may remember in math that you've talked about permutations and combinations. This is what we call a combination. And so they tend to look like n, c, k. And n is the number of trials, and we're choosing k different ways to arrange them. So how many different ways can we do this? And since this is known as a combination, we can actually find that under the probability menu in our calculator. So you go to math, you arrow over to probability, and then you choose the NCR for it. So if you wanted to figure out so if I have 5 trials, I want to know how many different ways I can have 2 successes. On my calculator, it would look like this. So let me pull up the calculator on the thing. So I would type 5 first, I go into math, I arrow over to probability, I go down to NCR for my combination, and so I have 5 trials, and I want to figure out 2 successes. So there are 10 different ways I can have 2 successes and 5 trials. And it keeps us from having to do what we call a sample space to figure out how many, especially when we end up with hundreds of different ways. And so how could I figure this out by hand? A 5C2. So 5C2 by the formula is 5 factorial over 2 factorial times 5 minus 2 factorial. And so this simplifies to be 5 factorial over 2 factorial and 3 factorial. And you'll notice that the bottom 2 numbers should always add up to be the top. Now, how do we actually work this out if we wanted to calculate this by hand? So 5 factorial is really 5 times every number below it. So 5 times 4 times 3 times 2 times 1. And then 2 factorial is really 2 times 1. And that's being times by 3 factorial, 3 times 2 times 1. And this is the one thing I like about writing out combinations is we get a lot of canceling happening, and so then it makes it easier to calculate. So what I end up with is after I cancel, I get 20 over 2, which tells me I get 10 combinations of 2 successes. And so why is that important? Because we got to figure out how many different ways I can get that value so we can calculate the probability. So the binomial coefficient counts the amount of ways, so the number of ways which k successes can be arranged among n trials. So why do we do that? Because I could have success, success, failure, 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 or I could have success, failure, success, failure, failure. And instead of having to go through those and mentally calculate how many different ways can I do that, we have a formula that allows us to calculate that. And so we take this binomial coefficient and we times it by the probability. So now we get this idea of the binomial probability, which takes this binomial coefficient we just talked about, and then it takes the probability of success to the k power. And so remember, k was the number of successes, and then 1 minus p, which is my probability of failure, times the n minus k power. And so how this would look like. So let's say I'm going to choose 5 students, and I want to know what's the probability that 2 of them will have an A. And so my probability, let's say, my probability of success that a person has an A, so let's say 1/4 of the class has an A. So to calculate the binomial probability, I have out of 5 students, I'm going to choose 2. And what's the probability that exactly 2 of those 5 students have an A? So 5 combination 2 times my probability of having an A is 0.25. I want exactly 2 students to have that. And then I want 3 students to not have an A. So this is the probability of failure, not having an A. And I want 3 to have that. And I want 2 to have the A. And so that allows me to calculate this. And then we calculated earlier that 5 combination 2 is 10. And so going through that will allow me to calculate what is that true probability. So I'm going to go ahead and calculate that on my calculator right now. 10 times 0.25 to the second power times 0.75 to the third power. And there's a 26.37% chance that exactly 2 people in the group of 5 I would pick would have an A. Okay, so let's go on to some real examples. So our next problem. Each child of a particular pair of parents has a probability of 0.25 of having blood type O. Suppose the parents have 5 children. So 5 children, that means our N is 5 trials. The probability of having type O blood is 0.25. Find the probability that exactly 3 of the children have type O blood. So I want to find the probability that X is 3, that 3 children have type O. So I'm going to do, I have 5 children, and I want to know the probability that 3 have type O blood. The probability of success of having type O is 0.25. I want 3 of the children to have that, which means probability of not having type O blood is 0.75, and I want 2 of the children to have that. So remember, this is my binomial coefficient, 5/3, so this is a 5 combination 3, which we could calculate out by hand. But I'm going to use my calculator. And I find out that to be 10 times my probability and this will tell me the probability that exactly 3 children will have type O blood. And that is 0.08789. And we can leave it as a proportion, or we can turn it into a percentage. It doesn't matter. Just if you're going to turn it into a percentage, do not make a mistake, because that will deduct you points. Okay, so that's how we figure out the probability that exactly 3 of the children have type O blood. So now the question turns into, should the parents be surprised if more than 3 of the children have type O blood? So I need to figure out the probability that more than 3. So I would figure out the probability that 4 have type O blood, and I'd add in the probability that 5 have type O blood. And I add those together to figure that out. So this is going to turn into a 5 combination 4 times 0.25 to the 4th times 0.75 to the 1st plus a 5 combination 5 times 0.25 to the 5th and 0.75 to the 0 power. And so now we have to calculate that. So a 5 combination 4 really is 5. There are 5 different ways of having that. Times the 0.25 to the 4th, times 0.75 to the 1st, which is just 0.75. Then I'm going to add in the 5 combination 5, which is really just the number 1. There's only one way, all of them having type O blood. And then 0.25 to the 5th power. And then anything to the 0 power mathematically is really the number 1. So 0.75 to the 0 power is really just 1. And so now when I go ahead, I'm going to get 0.01465 plus 0.00098. And I add those together, and I'm going to get 0.0156, which as a percentage is 1.56%. So should we be surprised if more than 3 of their children have type O blood? Yes, we should definitely be surprised. There's only a 1.56% chance that more than 3 would. Very surprising. Okay. So how to calculate binomial probabilities on the calculator. So I put this in here because I realized that in your notes you didn't have this. So I will put this on the website as a little thing that you can print off for yourself. But you can do this on the calculator. So if you want to figure out what's the probability that you get an exact number. So what's the probability that I get exactly 3 kids who have type O blood? Then you're going to do this, the probability that X equals a number. And with that, that's going to be a binomial PDF on your calculator. And the way you type it in is binomial PDF, number of trials, probability of success, and the number value from your probability. So where is this? This is in the distribution menu. So anytime you're calculating probabilities on your calculator, it should be in the distribution menu. And so usually that's the second VARS button. And that's how you get into your distributions. That's where your normal CDF is. And so now that's going to be where your binomial PDF is. Now, if you want to know, because as you can tell on our last problem, when we had more than 3, we had to do exact probabilities multiple times. This one was only 2, but sometimes you'll have to do like 10 of them. And that's a lot of calculating that you have to do. So there is a binomial CDF that allows you to do multiples, but it only does less than or equal to. It does not do greater than or equal to or just less than. So if you have a less than or equal to, there are multiple different things that you can do for that. And so here's just kind of guidelines that I wrote up. This is going to be the binomial CDF. And when it's less than or equal to, you can just type it in as is. There's no changes that you have to do. So you do a binomial CDF, the number of trials, the probability of successes, and the number value from your probability. And so this is saying that you want X is less than or equal to whatever that number is. But if you want greater than or equal to, because the calculator only calculates less than or equal to, you now have to do a little bit different of a formula. You're going to do 1 minus the probability X is less than or equal to the number minus 1. Since this number is included here, I cannot include it over here in that binomial. So I want everything lower than that, so the next one lower is the number we put in here. So it's going to be the number minus 1. And so the way we type it in our calculator is we go ahead and we type 1 minus, then we go to the distribution menu, do binomial CDF, the trials, probability of success, and the number value from the probability minus 1. So if I wanted to know the probability that x is greater than or equal to 5, then I would do 1 minus the probability that x is less than or equal to 4. So I drop down by 1 because I want to include the 5 in that leftover part. Okay, now if we want the probability that x is greater than or equal to a number, then I do 1 minus the probability x is less than or equal to the same number. Because this number is not included here, I can include it over here. And then if I want to calculate the probability that x is less than the number, then I'm going to do a binomial CDF, and I'm going to drop down 1. Because this is already less than, and remember our binomial CDF calculates less than or equal to, because CDFs only calculate less than or equal to, and if I only want less than, not the equal to part, I have to drop down a number. And since these are all whole numbers, it's okay to just drop down one whole number. Okay, so let's walk through a couple problems just to see how this works. So when I'm rolling 2 dice, the probability of rolling doubles is 1/6. So here's my probability. Suppose that a game player rolls the dice 4 times, so that's my n, hoping to roll doubles. Find the probability that the player gets doubles twice. So I want the probability that we get doubles twice in 4 attempts. So this is going to be a binomial. Because I want exactly 2, it's going to be PDF. When I want a less than or equal to or greater than or equal to, that's where I'm going to use CDF. But because it's exactly a value, we're going to do binomial PDF. And then we're going to put in the number of trials. So my trials is 4 times. My probability of success is 1/6. And I want to know that x is equal to 2. And so we're going to put that in our calculator. So let's go ahead and look at that on the calculator. See how that looks. So I'm going to turn on the calculator. I'm going to go into the distribution menu. I'm going to go down to binomial PDF. So here's my binomial PDF. My trials was 4. My probability of success was 1/6. And my x value was 2. And I plug it in, and it gives me my answer, 0.1157. And that's it. So now, should the player be surprised if he gets doubles more than twice in 4 attempts? So I want to know the probability that the number of successes is more than 2. So not 2 or more, but more than 2. So because I can only calculate less than or equal to, I'm going to do 1 minus the probability x is less than or equal to 2. So I'm following the guidelines of this problem right here. Nope, not that one, this one, sorry. Because 2 is not included here, I can include it here. It's got to be in one or the other. And so now I'm going to do 1 minus the binomial CDF and then my trials is 4 again. My probability is 1/6. But now because it's a CDF, it's going to be x is less than or equal to whatever number was from here. And so let's go ahead and do that on the calculator. Okay, so let's exit out of there. So I'm going to start with my 1 minus, because I'll forget about it later if I don't do it. Distribution, we're going to now do a binomial CDF. My trials was 4. My probability is 1/6. And my Y value is 2. And see, it calculates, see how it has the 1 minus the binomial CDF? So it calculates that for you. And so that is 0.0162. And so should we be surprised? Definitely. There's only 1.62% chance. Yes, we should be surprised. And so all of this work supports our answer and justifies our answer. Okay, one more sample problem. Okay, to introduce her class to binomial distributions, Mrs. Desai gives a 10-item multiple choice quiz. The catch is her students must simply guess an answer A through E for each question. Mrs. Desai uses her computer's random number generator to produce the answer key, so that each possible answer has an equal chance of being chosen. Patty is one of the students in the class. Let X be the number of Patty's correct guesses. So let's go ahead and make sure that this is a binomial random variable. So B is it binary? So my success means I get it correct. A failure would be incorrect. Independent. Does getting the one question wrong affect me getting the next question wrong? Because these are totally random and all of that. These are truly independent. It's a random assignment. Assures independence. N, number of trials. So it's a 10-question quiz. So my trials is 10. S, probability of success. Since I have answers A through E, that is 1, A, B, C, D, E, 5 choices. So the probability of success is 1 out of 5, or 0.2. So now what we're going to do is we're going to find and interpret the probability X equals 3. So I could calculate this by hand, but we've got our handy dandy calculator, and since this is X equals 3, this would be a binomial PDF. My trials is 10. My probability of success is 0.2. And I want to know that I get exactly 3 correct. So we're going to go ahead and calculate that on our calculator, and we find 0.2013. So now it also says interpret that. So what does it mean? That means that there is a 20% chance that Patty will get 3 questions correct. And that's exactly 3 questions. Okay, to get a passing score in the quiz, a student must guess correctly at least 6 times. Would you be surprised if Patty earned a passing score? Compute the appropriate probability to support your answer. So my probability is that X has to be at least 6. So greater than or equal to 6, which makes sense. 6 out of 10 give you 60%. That's a passing grade. Anything above that is passing, anything below that is not. Now remember, I binomial CDFs only calculate less than or equal to. So I have to do 1 minus a probability that x is less than or equal to. And so since 6 is included in here, I can't include it in what I'm subtracting. So I have to drop down 1. And I'm going to do 1 minus the probability that we fail. So we get less than 6. And so that means I'm going to calculate 1 minus the binomial CDF of, let's see, we have 10 trials. My probability of success is 0.2. And I'm going to have x is less than or equal to 5. So 5 is going to be the number inside. And when I calculate that, I get 0.00637. Which gives me a 0.637% chance of passing. Which means those people who get those Scantron final exams don't even look at it and just randomly bubble in stuff, only have a 0.637% chance of actually passing. And that's it for today.